Okay, so good evening to all, and thanks for joining. This is the interactive session for our course Foundation Engineering, taken by Professor Kousik Deb from IIT Kharagpur. I'm one of the TAs, Kashyap Vasudevan, and my fellow TA is Shivshankar Nandi. I hope we have all of us have gone through those videos of week 4, and so we'll be discussing a few problems today and dealing concerning those contents, and hopefully, yeah, I would encourage uh, who- like all to participate wherever. If you have any doubts or if you want to share something, please feel free to interrupt and or ask at the last. Anything is fine. Okay, so I guess, yeah, so let's begin. Okay. So just for a little recap, what we did in the last week. So week 4 uh, deals with the settlements of foundation, especially the shallow foundation. So our the thing is, like, the whole idea is like, the last week we discussed about shear strength. That is, we were trying to find out the bearing capacity of the soil with respect to shear strength. But this week we are trying to also get the aspect of settlements, because settlement is also something which controls the safe bearing capacity, the allowable bearing capacity. Because many a times, even if the failure has not happened, settlement would have been quite high, and we will have to in order to control the settlement for serviceability, we will have to check the settlement also. So the idea is to figure out the settlement of a shallow foundation. So when we say shallow foundation, settlement of shallow foundation, we can define different deformations of shallow foundation in different ways. For example, one is uniform settlement. So uniform settlement, we all know, it's that is when we have the same amount of settlement throughout the base of the footing or the foundation, wherever. So uh, in a way, it is the safest foundation one can have, because there will be no structural damage to the to the our construction, like constructed structure. So since the whole structure is settling uniformly in all the at all the points, there won't be any additional moment or shear force developed due to the differential settlement. So uniform settlement is fine, but if it is very excessive, again the serviceability issue will be an issue, problem. For example, uh, there are many cities which lies on lake beds. For example, one of them are Mexico City. So if you go through the problem, geotechnical problems that they face there, so there are buildings that has gone. The complete building has gone settled for a huge amount, like half a floor or one floor, and they have to modify. Though the structure is intact, there is no cracks. Even there is no little crack on the structure. The whole building has come down because it's the whole thing is on the same lake bed, and the stresses below the building is the same. So because of these things, uniform settlement can happen. Though, so even though it's safest among all the other things, but there is an upper limit for that. So we need to take care of that. Angular distortion is nothing but when we have multiple footings in the same structure, especially for framed structures. One of the footing might settle in one way and the other might not settle that much, and we'll have a differential settlement between the two footings, and this can cause our additional moments and additional shear force at the joints of the at our joints of the frame of beam column joints, etc. So this is a very big issue, because even a small settlement can cause a big moment in our frame, depending on the length of the beam and all. Another thing is the tilt. Tilt is means the whole structure is tilting. So if we have a raft footing or a mat foundation, it may be for different reasons. The properties of soil might be different at different points. and the load stresses that is acting could be a little different. So because of that, the whole structure will tilt, which is also an issue because once it tilts, the stresses are different at the bottom. Even if we are not expecting any, even if we don't expect any structural damage, if it the stresses at the base is different now once it tilts. At the lower end, there can be higher stresses, and at upper end, there can be tension also. Tension is a very disastrous thing when it comes to concrete or soil. So that is the three different ways of putting the deformations we encounter with shallow footing. And when we say settlement, we have to mention these three settlements. Like so there is a immediate settlement, there is secondary sorry primary consolidation settlement, and there is secondary consolidation settlement. Now the relevance of these three are: the first one is also called elastic settlement, because what happens is like the moment we load, it will due to its elastic properties, whether it is whatever material it is, it will have some elastic properties. So because of that, there will be an immediate settlement because of the material property of the so this deals with elasticity, which is material property. And second one is primary consolidation. This is exclusively for clays, right? So consolidation happens in clays, which is time dependent. So this happens in clays, both normally consolidated or over consolidated. The idea is like the water escapes out, and the volume of water escapes contributes to the settlement. So that is the idea. So okay, so the other thing, secondary thing is like this is a consolidated settlement. This occurs in organic clays towards the end of the settlement. We assume that it happens at the end of the after primary consolidation. This begins. That is assumption, but in reality, it can begin the moment it is loaded. So organic content, when there is too much organic content, this can happen because of the decomposition of the organic matter. Also, rearrangement of particles. These two things can contribute to the secondary consolidation settlement. So when we talk about these things, all soils may not show these three settlements. So for example, sand primary only deals with immediate settlement. It's quite intuitive, right? So because consolidation doesn't happen in sand, so the immediate settlement is the thing that is the most of the settlements. Like I could say that 100% is immediate settlement because of the elastic compression. Now clay can have immediate also, primary consolidation settlement also, and secondary also. But the secondary thing is exclusive for organic matter, and also sometimes for due to the rearrangement. So we understand that. But the idea is like this. This is the highest contributing among the three for clay when it comes to clay, because as immediate settlement is not that much. Okay, then after that we moved on to the corrections for different settlements. So the thing is like there are different things that we have to consider which influence our settlement. For example, depth. In order to normalize our settlement for different depths, we assume it to the ground level. To bring it to the ground level, we can take this depth factor. And rigidity. The thing is like when we have flexible footing, that is any isolated footing, it can have a, depending on the column position, it can have different settlements at different points, right? So at the middle it will be the highest, but when it is a rigid footing, it will settle in the same, it will be a uniform settlement. So the idea is like if we are dealing with a rigid footing, for example mat foundation or raft foundation, we'll have to consider that. So we'll have to reduce it a little bit. And the other two corrections are pore water pressure, or it can also taken care by the correction to consider effect of 3D consolidation. So if you remember, the equation for consolidation was derived from Terzaghis 1D theory. And so but in our real world the footing is under the 3D condition, so the consolidation is happening in all the directions. So we have to consider that this particular correction for that. Then we moved on to different ways of calculating the settlement. And in that, the primary thing is this plate load test. This is a very important test because of the obvious reasons. As I told before, till now we were dealing with shear strength of the soil in the last class. We were finding the safe bearing capacity, SBC and all, with respect to the shear strength. And this week we were dealing with settlements, with respect to settlements. So what plate load test is, okay, so we have one more, we'll have one more bearing capacity using settlement. So the among these two we have to take the lowest value, lower value. That will be our allowable bearing capacity. So this is the capacity we will be reporting to the structural engineer to design the foundation. This is very important. So plate load test, what it does is we get the relation between load and settlement. So once settlement comes into picture, we can get for our required settlement requirement, the tolerance. Each structure will have different tolerance. So for our particular tolerance we can find what is a load acting on the plate, and from the plate we can arrive at the pressure at the footing. So indirectly we are getting the bearing capacity. So bearing capacity of these two criteria, where the lower value will be taken as allowable bearing capacity. So this is a very useful particular test, especially for site investigation. If you are going like if you are ever involved in these things, this we have to keep in mind. Procedure and analysis both were both were discussed in detail the last week. And the next like this is the highest, this since this is dealing with field test, this has the highest what do you say, this gives a better prediction for the settlement. Now we have like if we are not able to do plate loaders, we have other ways also to find out the settlements. And another that one is one deals with SPT. From SPT we can directly get our settlement values. These are like based on correlations. As I told earlier, like correlations has its own disadvantages, limitations. So anyway, this is also useful. In IS code, the graph is shown which relates SPT value and our width of the footing to the settlement that can be expected. Then we have static code penetration test correlations, both given by D. Beer Martins as well as Meyerhoff. It's a very similar correlation, uh, from which we can arrive at our settlement. And there is one more semi-empirical method given by Boisman. That need not, that doesn't even want any field test values. We can directly arrive at the settlement. Okay, so this was the things that were discussed. So before, okay, so let's jump on to the first question. But uh, okay, so the first question deals with plate load test. So we have a plate load test, and it's a granular soil. We know that the plate load test is like works better for granular soil. So we have a dimension 60 centimeter for the plate. We also have a dimension for foundation. 5 plate settlement was found out. Settlement was found from the load settlement curve for the expected foundation load of 120. So this is the foundation. We have the plate settlement. So plate settlement is given here. What would be the estimated foundation settlement? So we are supposed to find foundation settlement if the water table is at 2 meter below base of the foundation. Okay, base of the foundation. And okay, So we are supposed to find the foundation settlement. Use Terzaghi and Peck's equation for calculating the settlement, and IS method for water table correction. Okay. So before we jump into the questions, first let us see the equation which is important here. Here, as they have asked, okay, as they have asked the Terzaghi and Peck equation. This is the Terzaghi and Peck 1948 equation, which relates our settlement of footing and settlement of a plate. So see, so we have set this. This is the settlement of plate SP, settlement of plate, and the suffix F indicates footing. So settlement of footing. So similarly, we have other terms which are this width of the footing, that is BF. BF is the width of the footing and BP is the width of the plate. So from this equation you can directly understand this is an empirical, because we have 30 just like that, so that units are important. Here we have to substitute the unit for width of the footing with centimeter, so we should not forget that before we use it. So having said that, this particular equation is only meant for granular soil. If it is a cohesive soil, we can directly take it as BF by BP in the RHS instead of the whole squaring and thing. Okay, okay. Then let us first solve this. We have to find the settlement. So in the question we have SF. So sorry, SP. We have SP is equal to 5 mm. BP is equal to 60 centimeter. BF, that is the width of the foundation, is 3 meter, that is 300 centimeter. So we can directly substitute this in the equation, right? So SF by 5. 5 I can write directly in mm, because whatever value I'll get for SF, that will be in mm, because this is a ratio, it doesn't matter. In the RHS we have BF by BP, right? So BF is 300 by 60, and at the numerator we have 60 plus 30, and the denominator we have 300 plus 30 whole square. This comes out to be like, if you solve this, SF will be as 9.297 mm. Okay, so we have the settlement of the footing, but we have to find the correct it for water table also. So when we correct it for water table, they have specifically mentioned it has to be in IS method, IS code method. So let us see what it is. So we have, when we say water table correction, there are two methods. One is given by Peck, and another one by IS, Peck, Hansen, Thornburn, and it's very similar equation, but the only thing is, like, one is with reference to the, this is reference is, the reference level is at ground level. Here the reference level is at foundation level, footing level. When I say reference level, in the sense we are measuring this dW, dF. dW, of course, we know that is the depth of the water table. dF is the depth of the footing. So all these things are measured from the ground level. Here it's measured from the foundation level. Let me write it as FL. Okay, so here we have CW. CW is it's very similar to the water content correction that we had, sorry, not water content correction, water table correction that we had used before in our Berry capacity equation. For the third term, that half B gamma N gamma, we had modified it as a W dash, if you remember, in IS code method. That is the same thing here. Instead of W dash, we are writing here as CW. So CW is equal to 0.5 plus 0.5 D dash W by B. Here, if you look at it, it's quite clear that it's an interpolation between zero point 0.5 to 1, depending on our position of water table. So in the equation, it's directly given, in the question, it's directly given that foundation settlement if the water table was 2 meter below the base of the foundation. So we directly have this dw as 2 meter, dw dash is equal to 2 meter, and b we already know it's the width of the foundation, that is 3 meter. So our cw will be 0.5 plus 0.52 by 3. This comes out to be 0.833. So our corrected corrected settlement is equal to 9.297 into 0.833. This will be 11.16. Okay. So that's it. So if we had this particular Peck and Hansen, the only difference will be dw will be measured from the ground level, and df also will be measured from the ground level. Okay. So what is our final answer is 11.16. One of the option, yeah, the one of the option is 11.16. Okay. So even if this question was extended to Peck Hansen, I hope you will be able to do it, because ground level they have okay, they have not mentioned ground level. If they had mentioned ground level, that or the depth of the footing, we can directly write this. Okay. Uh, so I hope the first question is clear. Now let's move on to the second question. Second question deals with okay, consolidation settlement, that is primary consolidation settlement. So let us just go through the question. We have a okay, sorry, we have a footing which is rectangular, and thickness of the clay is mentioned. It's normally consolidated clay. Underlain is by a rock layer. Okay, and depth of the foundation is given. This is expected load intensity of the foundation. So the load intensity is given. Properties of the soil. Okay, we have submerged. This is CC we have, and initial void ratio also we have. Water table was at the ground level. So find the expected primary consolidation settlement. So primary consolidation settlement we are supposed to find considering 2:1 pressure distribution. Okay. So at this stage we are not told to apply any correction corrections. So in this question they have mentioned. So we will stick to that. Before that, let's just recap this equation involved here. These are the two equations that we use for settlement. If you have gone through this before, it will be a repetition for you. But let me just explain it very quickly. There are two equations that we can find it for primary consolidation settlement. That is, these are the two. One involving CC and one involving CC, that is compression index, coefficient of compression, and E naught and all are there. And otherwise, we have coefficient of volume compressibility. Okay, so first let us say let us just be in the same page. CC is nothing but coefficient of compression index. Oh, sorry. Coefficient of compression index. E naught we know it's the initial void ratio. And P naught P delta P is nothing but our we had in the earlier classes I used these symbols. This is sigma dash naught and sigma delta sigma. It's nothing but the effective overburden pressure. So sigma dash is the initial effective overburden pressure. Delta sigma dash will be the increase in overburden pressure, or increase in pressure due to our footing. So that is a change that is happening. So our delta sigma or delta P deals with the increase in our load. So that is a this is H is the uh, I can say thickness of the clay layer. But many a times if the clay layer is very thick, with when you compare it to the width of the footing, so we'll have to take a different value of H that will come to it later. uh, and Otherwise you can also define it as the effective depth of clay layer which is available for which is undergoing settlement. So when we have a very thick layer, the whole layer does not undergo such a treatment. Only at the top, just below in the influence zone, only the settlement occurs. We'll come to that in the coming slides. So the second equation deals with the coefficient of volume compressibility. That is our MV. So we have this equation. How this equations came into existence is quite simple. If you are plotting this compression curve, we have the slope of the curve as Cc, that is nothing but our delta E by log of sigma final will be the sum of initial plus the change in our load by initial. So this equation we have, plus we can write delta H by H for 1D consolidation as delta E by 1 plus E naught. If we club these two equations, we can arrive at this. Okay. Sorry, we can arrive at this particular first equation. The second equation is nothing but MV is defined as delta E by delta sigma 1 plus E naught. So this equation and this equation, these two equations, if you club, you will get the second one. So having said that, the data we have at this point is Cc and E naught. So the data we have is Cc is equal to 0.3 and E naught is equal to 0.9. So we can use the first equation here. So okay, so using the first equation, we can write this is at ground level. Groundwater table is at ground level, and this is a rock base that we have. The foundation level is at what was the depth? 1.3 meter. So the total thing is 5 meter. Foundation depth is 1.3 meter. So what is our thickness of the clay layer available for settlement? That is 5 minus 1.3, that will be 3.7. Now as I told before, we have E naught Cc are constant. That is, there is nothing to worry about it. H is the thing that we are here. The influence zone. What is influence zone? We'll come to it in the coming slide. Influence zone is taken as 2b from the base of the footing. So base of the footing is here. It is 2 meter, right? 2 meter. The base of the footing. Yeah. So width of the footing is 2 meter. So our 2b will be 5. Sorry, not 5. 4 meter. And if you see 4 meter plus 1.3, it will go beyond this hard strata. So our consolidation will only happen till here. So we can come at 3.7. Why this 2b, we will come to it in future. Now another thing here involved is our delta p and p dash. So let us come to that. Okay, so p dash, that is a sigma dash, that is overburden pressure. So we are trying to find the settlement at this point. Actually, strictly speaking, whatever we are going to find is here, assuming that we are taking the average for the whole clay layer which is available for settlement. So at the center, at the middle of the layer, we are considering trying to find the settlement. So that will be uh, so the stress at this point, we are dealing with the stress at this point. So that is like, so half of this middle layer will be 1.8785, right? So that is 3.7 by 2, 1.85 meter. So overburden pressure. So the thing details that we have is submerged, gamma submerged is 9 kilometer per meter. So overburden pressure is quite clear. We have 1.3 plus 1.85. So the depth is 1.3 plus 1.85 into gamma dash, that is our 9. This turns out to be 28.35 kPa. Okay, our last headache. This is the most important part in this equation. Sigma p, or sigma or delta sigma. This depends on how the load is getting dispersed from the footing to the deeper depths. So in this case, in the question, they have directly given 2:1 will be the pressure distribution. But that is actually debatable. That is the easiest way, but that is debatable. But since they have mentioned it, we can take it as 2:1. So if it is 2:1, our dimension, like the pressure distribution, will be along this length. So this length can be written as b plus z, or the dimension will be increased by the depth, if you recollect the classes. Because since this is our z, this part will be z by 2, this part will be z by 2, because it's 2:1, and the total will be b plus z. So our length will in the other direction will also increase by z. So okay, but we don't know the total load, right? We are only given the foundation pressure. So at the foundation we have q is equal to 50 kPa. So we can calculate the total load is equal to q into uh, l into b, right? That is 50 into 3 into 2, which is 300 kilonewton. So what will be the stress at this depth? So we'll have to consider the whole length of this, what do you say, at the middle layer. That is b plus z and l plus z. So that will be our change. That will be our change in the stress at our required layer, middle layer. That will be 300. That is a load. That will be the same. Divided by the new denominator, our 3 will be increased by, what is the z here? Z is nothing but 1.85 for us. So 3 plus 1.85 and 2 plus 1.85. That is the length and breadth, both will be increased by the 1.85. And this turns out to be, if I'm not wrong, 16.06 kilonewton per meter square. So we have all the terms now. Now it's just about substituting. So S can be written as zero point 0.3, that is our CC value. 3.7, that is our H, that is a thickness of the clay layer which is available for settlement. And 1 plus E naught, E naught is 0.9, log of sigma, that is 28.35, plus delta sigma is 16.06 divided by 28.35. This comes out to be 0.113879. So whatever whatever unit we are giving for the height of the thickness of the layer, that we'll get. So this is in meter. So we can write this as, we can write this as 113.88 mm, right? So one of the options are, yeah, 140. Yeah. So that's it. Here, so this equation is very important. It's when it comes to consolidation of clay, we need to be, this must be there at our disposal all the time. So all the terms should be clear. Here, the thing that we need to understand is this load dispersion. So since this is 2:1, we have to add this particular length at the bottom, that is z by 2 and z by 2, that will become b plus z. And also since it is 3D, in the length direction also there will be dispersion, that will taken care by l plus. That's why we have taken the new. So as you go deeper and deeper, the increment in stress due to the footing will be lesser and lesser, since the denominator will be increasing. L plus Z will be, and B plus Z will be higher. Okay. So okay, so let's move on to the next question. If okay, so again, if you have any doubts, please feel free to interrupt me, or if you want to ask anything, it's fine. Moving on to the next question. The next question deals with estimation of settlement itself. So let us see. We have an isolated footing which is square footing, okay, and depth of the footing is 2 meter. Sand deposit. So this time we have sand. Till now we were discussing about clay. Now we have sand, and column load is directly given 1500 kilonewton, and thickness of the sand layer is 12 meter. Okay, so here the thickness is quite considerable when it comes to the dimension of the isolated footing. So we will come to that, how it turns out. And properties of sand are given. Gamma is given. Cone's resistance. So as we had discussed before, from cone resistance we can arrive at the settlement. There are different correlations, two correlations we discussed, and actually they have told us to estimate the settlement using Meyerhof, one of the methods. They have told water table is at the base of the foundation. Okay, consider gamma W. Okay, do not apply corrections. Fine. So uh, so yeah, this is the equation involved here using standard penetration test. So we have talked this before. We have different correlation for SPT and SCPT. Static cone penetration test, using that we can use this equation. That is, here H is, as we had discussed before, thickness, or the thickness available for settlement. Soil layer, I can write. C is the compressibility coefficient. So this is a new coefficient, that compressibility coefficient. So this is a factor that we Meyerhof and De Beer and Martens have different values for, different equations for. So the rest things are same. We know that sigma dash, sigma bar or sigma dash is nothing but this effective overburden pressure. So delta sigma is the same thing that we had discussed before. So the other thing is QC. In both the equations are very similar, only this coefficient is different. QC is nothing but the cone resistance that we have, that we are given here, that is the cone resistance. And this sigma dash is again overburden pressure, effective overburden pressure. So so let's jump into the question how it is. Um, we have the ground level here. The water table is given. So this depth is same as the depth of the footing. I think that is 2 meter. Okay, depth of the footing is 2 meter. Okay, and load that is acting is 1500 kilonewton, and the total depth that we are dealing with is 12 meter. So that's what we are talking about now. When I say 12 meter is quite high, so we cannot take the whole 12 minus 2, 10 meter as the thickness of the soil which is available for settlement, because as I told before, that influence zone. Now what is influence zone? So our influence zone is 2b. That will be our, what is our b here? That is width of the footing is 3 meter. This is a square footing, so 3 into 3. So this will be 6 meter. So this, only this is the influence zone. So influence zone, how did we get is, like if you draw the pressure bulb below this footing. So when I say pressure bulb, it is a line which represents the uh, same pressure. So there are different pressure bulbs for different pressure levels. So if we plot pressure level for 10%, that is, if this is Q, at the top we have Q, 10% of Q, if we draw a line which is joining all the points which has 10% of Q, that depth will be 2b for square footing. For strip footing and other shapes will be different, but this is the significance. So 10% of Q is considered the limit. Beyond that, we are not neglecting it. So if we plot that, that will be 2b. That's why we are considering only 2b of the from the base of the footing. So having said that, uh, this shape and all can be obtained from different pressure distribution theories. The most famous one being Bosnian theory. Okay, so having said that, we are interested only till 6 meter till the bottom. So uh, the rest everything is similar. What we have H we know C. Okay, so I guess we can directly write it. Uh, so our settlement. So H will be 6 meter, right? Only 6 meter is available for settlement. Our C value, okay, so we have to find C value, right? C is equal to 1.9 by Meyerhof method, 1.9 QC by sigma naught. Oh, so I forgot to find sigma naught also. Okay, sigma naught. What is sigma naught? Sigma naught is the pressure that is at the middle of this layer. That means our this distance is 3 meter. So our uh, sigma naught will be this is the initial. So okay, sorry, sigma naught we are talking. So we are just talking about the overburden pressure before the footing. So sigma naught is equal to just the first, this gamma w is nothing but 19 kilonewton per meter cube. We can conveniently take it as gamma sat also. Sorry, not gamma w. This is gamma bulk. Gamma is equal to 19 kilonewton per meter cube. So we can assume that gamma sub is equal to 19 minus 10, that is 9 kilonewton per meter cube below the groundwater table. So first 2 meters it will be 19 into 2 plus 10 minus, sorry, 19 minus 10, that is our gamma submerged, into 3. This turns out to be 65 if I'm not wrong kilonewton per meter square. Okay. So in this equation we can write 1.9 into what was our QC. Cone resistance is 11,000. So 11,000 divided by 65. 65 is our overburden, effective overburden pressure. This checks out to be 321.54. Okay. So we have 321.54. What are other things? We need delta sigma. So delta sigma, as I told before, delta sigma, in order to write that, we need this distance. This distance is nothing but b plus z, right? So 3 meter plus the depth. So b is 3 meters. So again this 3. So our load is 1500 divided by 3 plus 3. Since it is square, again 3 plus 3. That will be uh, okay. That will be 41.67 kPa. So we have all the terms required. Now we can directly substitute in this equation. S is equal to 2.3 into 6, that is our H, divided by C value, that is 321.54 into log of, okay, let me write this properly. So the whole thing is 12 meter. Log of what is our, okay, 65 plus 41.67 divided by 65, right? So if you write this, the answer will be 9.233 mm. So this is the answer we have. Do we have? Yeah, we have a option 9.23. Uh, okay, so here we are not dealing with much things, so we can also extend it. For example, here they have not asked for correction. We have two corrections, right? Depth correction and the second one was rigidity. So sorry, rigidity correction. Rigidity correction. So rigidity correction, there is nothing much. There is nothing much of an issue. If you go to the IS code, you will find it's generally zero point 0.8. So whatever you're getting for flexible footing, if you multiply by rigidity correction, that is zero point 0.8. That will be our settlement for our rigid footing. So if we have a mat footing or a raft foundation of a width, we can first treat it as flexible itself, and whatever value we get for settlement, we can multiply it by zero point 0.8 and we get it rigidity settlement, settlement for rigid footing. So will not be that's quite generic. So generally it is zero point 0.8. If you for one more details, you can go through this IS code. And depth correction we can try, right? So though it is not asked here, let us extend this question to find that to correct it for depth also. So if you go to IS code, you will get this chart somewhere, yeah, for page 22 you will get this. This chart has a lower portion also. I have cropped it. Lower portion deals with deeper foundations, like for pile, I guess. Like you can use it for pile and all, but here we are concerned with shallow, so the upper half is enough. So let us see. We In the y-axis we have d by lb. So in the figure it is quite clear what is d and l. So let us see d by lb, root lb. In our case, d is 2 meter, right? And L and B, we have a square footing, so L and B both are 3. So I can remove the root also. 2 by 3 is 66.6, 0.667 something. So if we are plotting 0.66 in this graph, okay, the other factor we need is L by B, right? L by B, since it is square, it is 1. So each curve represents a different L by B. So if I'm drawing a line at this 6.667, we are like the it it meets at this one curve one at zero point 0.8. So I can write depth factor 0.8. So our this thing will be so our yeah. So our settlement can be corrected settlement is equal to 9.233 into zero point 0.8. That will be 0 point, sorry, 7.39 mm. Okay, so I hope you got the idea. um, so the purpose of this settlement, this correction, is like we are trying to get the settlement what will be happening at our so we are taking the reference as the ground level. So what if the footing was at ground level? So at ground level our correction factor is 1. So we are bringing all the footing to the ground level. We could say that by doing this correction. Okay, so having said that, rigidity I already told. So can we extend this question a bit more? So let us extend this with immediate settlement. So all these equations what we discussed here was dealing with immediate settlement. But for immediate settlement, we can also alternatively we can also use this elasticity equation, right? That we had discussed before. So elasticity equation is considered just as an alternative if we don't have any other option. So if we have this data, well and good, because more data we are using it from field or anything, the more accurate results we are getting. So, but if we don't have any other option, we can rely on our elastic equation. That is this thing. This is our elastic equation to find our immediate settlement for soil. Uh, okay. So when you look at this equation, we have different terms. Q is nothing but the applied pressure by the footing, right? So we know that. B is the width of the footing. Mu is the Poisson's ratio. That's generally we can take it as 0.5 for clay and zero point 0.3 for sand. Okay, this is a general values. In this here we are, since we are dealing with sand, we can take zero point 0.3. There are different tables in different textbooks and different codes that you can also refer for different Poisson's ratio. This is the modulus, elastic modulus. Elastic modulus, I guess we have already have it in the question. That is 25,000 kPa. So 25,000 kPa. Applied pressure, as I discussed before, we know that it's 1,500 and applied pressure will be 3 into 3, right? Width of the footing, that will be 166.67 kPa. And mu, I already told you, zero point 0.3. B will be 3. Another thing left out is this factor. So influence factor. So for different shapes and different position of the footing, we have different influence factors. So this particular table is from IS code itself. So they have taken this. So since we are dealing with square footing, and we are checking the um, settlement at the center, so we can take this 1.1. So our influence factor will be 1.12. So quickly finding the settlement, we can get SI is equal to 166.67 into 3, 1 minus 0.3 square by 25,000 into 1.12. This turns out to be 20.4. To this also we can apply our same influence factor we had obtained before. Sorry, not influence factor, the correction factor for depth. So if we are applying correction factor, corrected settlement will be 20.4 into 0.8. That will be 16.3. So you can see it's quite high value when you compare it to our previous when we used Meyerhoff's. So settlement is quite important in our design. So to make it economical, we have to get the correct settlement as much as possible. So it's though it is overestimating, there won't be any safety issues, but the material cost might be very high in our design. But in the absence of other data, we can use this. Uh, and again, in this particular equation, there are more assumptions, right? So this we are assuming it's an elastic material, and Poisson's ratio we are assuming it has to be constant. So this values has to be constant throughout. Influence factor is a big loophole. So these things we have to consider. Okay. So having said that, but here, if you notice, we have different core, center, average, and all, because uh, till now we were dealing with talking some more on this load distribution. I told you this particular thing is an assumption, 2:1, and we are finding the whatever depth we want. We are finding this just like this. So what is actually happening is we are taking the average, like the average stress throughout, because we are the whole load uh, we are dividing it by our increased length, right? So that is our L plus Z and B plus Z. Let us say if it is a rectangular footing. So in this case, this is actually uniform, but in this assumption, according to this assumption, this is a uniform. So if I am writing this as sigma naught, delta sigma naught, and if I am plotting it so delta sigma naught will be this thing. But in reality, that is not the case. In reality, actually, it will be like a little, I guess, a peak at the center and a lesser at the. So see, now the this thing is different. Sigma, delta sigma is different at different places. Sorry. So delta sigma will be different. It will be maximum at the center of the footing, and as it goes to the periphery, whatever depth we require, I'm talking about the same depth, we'll get a different sigma. So but we already know in our equation, settlement equation, we have CCH by this all, there is no issue. Sorry, E naught and plus log sigma naught by plus delta sigma. This delta sigma is varying now, right? So uh, at different depths, at different radial distances also, or different yeah, at different distance from the center, our delta sigma is varying, so our settlement will vary. So since settlement is varying, we will have a difference in settlement so at the top, sorry, at the middle it will settle more, at the edges it will settle less. So we might have something like this also. So my point is, when we consider this assumption, we have to remember that we are considering it as a uniform load. Actually, we are supposed to use this particular thing. So this can be, there are different pressure distribution theories. IS code encourages Bossinus theory. So for different loading, so here if we are talking about a flat plate load, there is an equation, and also for point load we have equations. So using that, since IS code encourages this Bosnian, we can you can go through it. So you'll get different. So whichever point we are interested in, we can, even outside this also, it will keep on decreasing. So at some radial distance it will be very insignificant as 0, and at whichever depth we require, because it's a function of z and r, the radius of the radial distance from the center and the depth from the footing level. So you can use this to find different stresses. Just to end it with a light question. Okay, we are already it's already time, so let me just do it very fast. So this is just a small question. Settlement of two foundations are 75 mm and 150. Okay, so this is, let us say this is 75 mm and this is 115 mm. How much is the angular distortion? It's nothing but the difference, right? So we have two different footings. One is settling more and than the other, so we will have an angular distortion. So angular distortion can be written as distortion can be written as the difference in the settlement, that is 115 minus 75 divided by the length, right? So the length which which is between these two footings and from the center line, that will be 5. So 5 meter is 5000 mm. This will be 1 by 25. This, the answer is this. So just to say that because the soil at this point and this point will be different, and its properties will be could be different, and this can be expected. So it's very catastrophic because this is also called as differential settlement. So what will happen is, like when we have a frame structure, if one is settling more, we will have a lot of moment and shear force involved here to resist this settlement. So this beam is under a lot of tension, and if it is a framed connection, all the beam and column will be under a lot of stress. So it will be like deforming like this. So that is a big problem. Our structures will fail very fast. Okay. Another thing that we discussed was this tilt. So when we are talking about tilt, initially, why this is important is like initially our, if our structure was like this, our bearing, you can assume it as sigma. But if once it is tilting, after tilting, it can go like this. Okay, sorry. So if our structure is tilting like this, our sigma minimum and sigma maximum comes into picture. We have to check that sigma maximum is less than SBC. Also, we have to be very careful that sigma minimum is not less than zero. It should not go. It should not go below zero, and once it goes below, that means it's tension, right? So sigma minimum should not go below zero, and we'll have to take care of that. So that's how this is important. Also, serviceability and stresses on the members, but this generally
Sir,
happens.
sound problem.
Hello, am I audible now? Hello,
Sir,
hello,
no sound here.
hello. Am I audible? Hello, can anyone respond?
Yes, sir, you are audible.
Okay, okay, thank you. Okay, so that's why it is important. So when we have tilt, we'll have to take care of this. There might not be any structural damage, but this can cause bearing capacity problems and all. Since this we have two different, suddenly we have two different stresses to take care. Okay, so having said that, just to conclude, this week is summarized in one of the slide. I'm pointing this particular slide because it has taken care of most of the things which was discussed in this last week. We have immediate settlement equation here, and we have consolidation settlement. These are the equations we discussed, and we have the four different methods to find immediate settlement for soils, granular soils. And in addition to this, we also have corrections that I had mentioned before, the depth and rigidity corrections. Okay, I hope things are clearer. Uh, and if you have any doubts, please feel free to share. This is supposed to be an interactive session, so that will be appreciated. Um, uh, like if you are hesitant to speak up, also you can type it in the comment box. I'll try to address it. If at all you get any doubts in between, you can always post it in our discussion forum. And yeah, so in this, I would like to point out one more thing in the lectures. If you haven't gone through yet, in the lectures he has discussed two three problems which are very interesting because he has taken bigger bigger problems and different cases he has done. For example, different corrections he has done. So please go through that also. That will be helpful. And yeah, so the next session will be by Shiv Shankar Nandi on the coming Saturday, same slot, 6 to 7. And mine will be next Monday, 29th, 6 to 7. Uh, yeah, so that's it. Thanks for joining. Have a nice day. And if you don't have any doubts, feel free to exit the meeting. Thank you.